Welcome, everybody. Thanks for joining us for tonight's presentation about the truly fascinating local mineral and gemstone benitoite. My name is Marisa Gomez. I'm the Public Programs Manager at the Santa Cruz Museum of Natural History, where you are all members, for which I would like to thank you. This series, our Collections Close-Up, is made specifically for our members so that we can help connect you to the collections that you help steward through your support. And before we get into the topic du jour, the collections items of the day, I also wanted to acknowledge the original stewards of our local resources, the indigenous communities of our region. The Santa Cruz Museum of Natural History resides in the traditional and unceded territory of the Yupi tribe of the Awaswas Nation. And today these lands are stewarded by the Amamutsin tribal band, who are working hard to fulfill their obligation to Creator, to care for and steward Mother Earth and all living things through relearning efforts and the Amamutsin Land Trust. And at this point, I'm going to introduce tonight's presenters. I am joined by Kathleen Aston, who is our collections manager, and Hilde Schwartz, lecturer at UC Santa Cruz in the Earth and Planetary Sciences Department, where she covers everything from dinosaurs to local geologic formations. So howdy, you two. Thanks for doing this. I can't wait.
Thanks for having me.
So we started by asking people joining us tonight to share their favorite mineral, gem, or rock. So I thought we could maybe hear from the both of you too. What would your answers be?
Okay, I'll go first. This is something I had to redecide today. I feel like I always am asking people about their favorite things, and then I'm never prepared with my own answers. So maybe I need to do a little bit of work on that. But I decided to go with gypsum today because I really like the shapes that it makes. And apparently that's when you get, when gypsum occurs in environments where there's sand, that's when you get like desert rose, those little rock structures that people really like putting in their houses, like me.
Your shirt's kind of geologic today too. So
thank you for noticing, Marisa. This is my shirt that I wear for geology themed events. Hilde doesn't know this, but when she gave the geology walk at the Californian Naturalist program, which I just finished, I was wearing this shirt as well.
Well, I would look through my pictures, Kathleen.
I think mine kind of like reminds me of granite a little too. I didn't do that on purpose, but maybe this will be my geology shirt.
Nobody told me about this, or I was wearing a better geology shirt. As we were talking about before, I think I'm going to claim my favorite mineral is ice, because I do like cold drinks. I really do. It's a fine mineral.
Yeah, so that gets me to my next question, because we're talking about a mineral tonight, benitoite, but we should probably make sure that we're all on the same page of what is a mineral. And you're now saying that ice is a mineral, which I know came as a shock to both me and Kathleen when we first learned this. So maybe, Hilde, could you school us a little bit and just share with us what is a mineral?
I think the basic definition of mineral is a naturally occurring substance that has a regular structure of the atoms that make it up, and a regular chemical composition, relatively uniform chemical composition. So what could be better than a mineral that you can make yourself in your freezer in your kitchen?
And you said naturally too.
So oh yeah, that's right. I guess if I make it, it's not natural.
Yeah, it's only natural if you go find it in
glacier makes it, it's natural.
Okay.
Correct.
Good. Thanks for clearing that up. So tonight we're going to be hearing from both of you. We're going to start with hearing from Kathleen, who's going to share a little bit about the history of our benitoite specimens, and the history of collecting benitoite, and then we're going to bring it back to Hilde to talk a little bit more about the mineral itself and how it's formed. All right, cool. And if you're joining us tonight, you can ask questions throughout using the chat. I will be happy to interrupt Kathleen and Hilde with your queries. So take it away, Kathleen.
All right, cool. Let me go ahead and share my screen. How's that look? Oh, wait. I have to stop share really quickly so that I can better organize my presentation notes. So it is important. Thank you for your patience, everyone. They were right here. just a second. It's interesting because we're going to be talking a lot about mining. And I hadn't, why laughter?
Because you're mining for your information right now, even as we watch.
Oh man, that wasn't even the pun I was trying.
Really?
Yeah, no, it wasn't. Although, okay. I was going to talk about, I hadn't thought about how like early people harvesting ice, or like before people had refrigerators and stuff, that would probably be like a form of mining.
Yeah.
Yes.
And it actually, yeah, it kind of was more, kind of looked like mining too.
Yeah, that is a new thought for me. Okay.
Did you find them?
All right. We're good.
Okay.
Thank you all for your patience. I just have to mess something up every time, you know.
Well, we got it out of the way early.
Yeah, that's what's important. Okay, so can you all see my screen and the Benitoite specimen on it?
Yes.
Yes.
Awesome. So we're starting with the collection's close-up with a little bit of context about the scientific discovery of Benitoite and the Benitoite specimens in our collection. So, you know, this guy has been a feature of our mineral displays since the 1980s, and we're really proud to be able to share it with you all. And then but to get started with the Benitoite story, I wanted to think a little bit more about just the context of what it means to be telling the story of like the first time that we're encountering a mineral or thinking about its use. And so we're focusing on that today, you know, and our story starts at the beginning of the 20th century for the most part today, but people have collected and used minerals in this area for millennia. For thousands of years. And a close to home example is something like this brightly colored cinnabar, which is a thing that would have been crushed into a powder and used as body paint by the first peoples of this area, and was traded across what is now the Western Seaboard, even as far as the Puget Sound. And so many of us probably know that cinnabar has another use, which is the creation of mercury. The New Almaden quicksilver mines, which were established in 1847 and operated until 1976, were once the richest mercury mines in North America. And one source has it that between 1850 and 1875, the miners there extracted a total of 46 million pounds of liquid mercury ore. And that was just, you know, a small chunk of the years that the mine was active. So this relates to our sort of next hallmark of mining history in California. So why the big desire for mercury? Gold was discovered, you know, at Sutter Creek in 1848. There's a number of different ways that people might be mining for gold, and Hilde is going to get into some specifics about mining, I think, a little bit later in the presentation. But of the ways that you're mining gold, you have methods that are placer mining, where you're just extracting stuff that's sort of like loose deposits that you're kind of sifting gold out of, to hard rock mining, where you're actually just like taking chunks of rock with gold in it out of the earth. So in this image here, you've got a sluice, which is a good small scale method for working with placer deposits. You're pumping a whole bunch of water and sediment through a structure like a trough, and sometimes it's built in a creek, sometimes next to it. And there's some holes and obstructions at the bottom. And then the slurry of like gold bearing material that you're like pumping into here is mixed with mercury, which binds to the gold particles, making them heavy enough to fall out below and then be collected. After they were collected, that mixture would be burned by miners, leaving just the gold metal remaining. So prior to the quicksilver mines going into operation in places like New Almaden and New Idria, which we'll talk about in a moment, you were having people import mercury from as far away as Europe, which was much harder to mine with. So, you know, there's a lot of booms and busts in the history of California when it comes to mining, but it's a common California story that, you know, someone's not doing well on their farm, they might decide to go out and prospect for gold or for other minerals. And so Jim Couch was a farmer who lived in Coalinga in the early 1900s who did just that. He went to this area, which is now so this is a little bit of a flash forward in time. It messes up my sort of grayscale color pictures we're about to go into, but this is the New Idria mining district, a ghost town now. In 2004 is when this photo is from. But it was a booming area of opportunity when Jim Couch decided to venture out there. And there's a few different stories of how he encountered the mineral he was about to discover, but a common one has him spending the night near San Benito Mountain and waking up to encounter brightly sparkling blue stones either in the ground or the water below him. And so Couch was grub staked, which is a word that you'll hear a lot if you look at the history of Benitoite, and a word that I at first thought just sounded really aggressive and not kind. And later learned that it was just a common term for when someone's going to front you the money to get some equipment as long as you share whatever you're going to discover with them. So Couch took his discovery, which he thought was sapphire, to his investor who grub staked him, R.W. Dallas, who immediately sent specimens to different professionals to take a look at it, and then also went back at the mine to pursue more of the substance. So at first people thought that the sort of like dark blue sparkly material might actually even be volcanic glass. Some people thought it was sapphire, also something called spinel, but it was a little bit softer than both of those. And finally, a piece of the specimen made its way to George Lauterbach, a UC Berkeley mineralogist, and lo and behold, it was something new. And I pulled these from like a couple of different decades, but you can see that two of these articles are from really early on. So George Lauterbach first reported on benitoite, which was his coinage for the new mineral, in a brief announcement in 1907. And it was picked up to fanfare here. And then you can see that even later on into the 30s and 40s, people were still talking about it. One article, which I didn't include here, which I thought was pretty interesting, was about an international meeting of scientists in San Francisco, I think in the 40s, who were meeting to talk about how science could be used to stop war. But first they were going to highlight a discussion of benitoite to talk about the exciting features of like scientific practice and discovery in California. So Lauterbach reported on benitoite, and then he, and one of the things, you know, Hilde's going to talk about a couple of the different, the various features of benitoite that distinguish it from other minerals. But one of the reasons that he knew it was a different mineral is by looking at its crystal structure. So this is a portrait of JFC Hessel, who was a Leipzig crystallographer, who in 1830 did some great math and predicted that there would only be 32 crystal clusters, 32 types of crystal structures even possible in nature. You can see that big old table kind of lists them out. And at that time, there were no known naturally occurring representatives of benitoite's crystal class, which is a di-trigonal, di-pyramidal crystal habit. And you can see this image far to the right in the slide is the first public drawings of those benitoite crystal structures from a paper that Lauterbach subsequently published, which you can see here, benitoite, its paragenesis and mode of occurrence. So these are from a 1909 scientific article in which he just described, he went out back, he went to the mine not long after he uncovered the specimen. He explored, he took a lot of notes, and this is his description not just of benitoite, but also the paragenesis is the set of minerals which were formed with it. And among those is waukeanite, which Lauterbach also named, and I apologize for the misspelling, under George Lauterbach's poster there. And you have this beautiful map of the context of the discovery. And another thing that is worth noting when this discovery was happening, it was a really exciting time, at least 2 new minerals, one also neptunite that we'll see later in slides, George Lauterbach originally thought was a new mineral, but actually had been previously discovered and named by a Scandinavian scientist. So no dice on that one. So we said that, you know, this, oh wait, is there a question?
Yeah, I was just curious, Kathleen, I'm not familiar with the term paragenesis. Can you clarify what that?
Oh yeah, so paragenesis, and maybe Hilde can like speak to this more clearly, is the set of minerals which are formed together, especially in a rock or with a like specified mineral. So that mineral and the things that are formed with it tend to co-occur with it.
Cool, thank you.
It means how all those things formed, how they formed together. What had to happen to make that work?
The whole story.
The whole story.
The whole geochemical story.
Yeah. Thank you for, I knew that was, I mean, that was a new word to me. And so I'm glad that we're able to stop and examine that more. Other things that were new in this paper, which is, I think, actually highly readable for something that was written more than 100 years ago, There's a lot of new photos, or the first photos, excuse me, of the Benitoite mining area, of miners. Oh, and one thing I did want to say is that, you know, by the time that Lauterbach actually got here to look at the area, you can see that mining operations were already underway. The first investor was like, I got sapphire, and started a sapphire mine, and then just kept going, being like, I got something, this is going to be useful to us. And the early techniques, you can see like some infrastructure here, but the early techniques involved pretty destructive methods of like dynamite and chisels. People were breaking off just big old chunks of what they were hoping to be gem quality crystals, so that they can later process them down from gem rough into things that they were going to sell as gems. And then let's see. Another image that's pretty cool and would probably have been even cooler in color from these early photos is the veins of benitoite. What you can't quite see here, which you would be able to see elsewhere, is the sort of like white coating of naturalite, which Hilde will talk more about later, but which covers, for the most part, all of the benitoite crystals you might be finding in this area. And as we said, early miners were mostly just interested in like pulling off these hunks, because they would cut that out later, when they could have just dissolved the naturalite in acid that wouldn't harm the benitoite, and that was just deemed to be too much of a time-consuming process for the kind of economic operation they were trying to run. So you can see examples here of these early drawings, again from the same article. The benitoite crystals, you know, set apart in the matrix, and then a portion of the vein that's split open. It's cool because these are like sort of this first time that this mineral was described for like the scientific community, and it's really like they're striking, but at the same time, if they had been color photographs at that time, things would have looked more sort of like stunning, and the blue color for which benitoite is well known and considered to be so striking. Was there a? I thought I heard something. Never mind.
There was a question that did come through, Kathleen, which is about, Mary's just curious if it's still found, but I think we're gonna get to that, like how people are still looking at benitoite. Yeah,
absolutely.
Cool.
And I think we'll talk about that. I'll talk a little bit more about you know, mining history, and then I think Hilde is going to talk a little bit more about even mining up to recent present. And so another thing that I wanted to just, you know, we're thinking about benitoite being this sort of receiving all this fanfare in the paper, it being so exciting because it's this new discovery and this instance of a crystal structure that had only been predicted, but also just being like, you know, sparkly and engaging and alluring. And apparently the federal government thought it would be alluring enough to use the work of looking at this crystal structure as a way to entice female scientists into the United States Civil Service. As we can see, Juanita Crawford Jr. here working as a geologist for the Department of the Interior. This is not something I have a lot of context for, but I thought it was a pretty interesting, like there's, you know, of the number of mentions that you find about benitoite, you see this instance of it being used to sort of advertise like women in science from an early period, which we know is a favorite topic of those of us here at the Natural History Museum. And so thinking more again about those crystals, so these cut crystals are from a great article called Benitoite from the New Idria District that kind of talks about all the different, like the history and the features of benitoite. And I just wanted to sort of highlight the difference between looking at these like cut gems and then these sort of more like mineralogical specimens. We talked a little bit about the Dallas mining operations, which blasted through the site from about 1907 to 1912, after which there was silence at the mines for a couple of years. And then it seems like, you know, folks had sort of gotten the low-hanging fruit of these like big chunks of crystals. But by the mid 20th century, folks were starting to comb more through tailings, look a little bit closer. People who were more interested in using that method we talked about of taking a specimen and soaking it in acid and like putting a layer of wax over the benitoite and other features that they didn't want to get etched away. And we're really lucky that people were interested in doing that because that's how we have the specimens that we're able to share with the public at the museum today. This specimen has been on display, as we mentioned, for a number of years already, and you can see the big blue chunks of benitoite. You can see some of the black little columns of neptunite, and then that sort of like white layer all over the blue schist that the whole thing is sitting in is natrolite. And I wanted to also add, we're talking about sort of the difference between people faceting these gems and then presenting them as like a cultural product versus having these sort of more mineralogical specimens. But these two had to be adjusted. You had to soak them in acid to get them to even reveal the benitoite within. So it's interesting, like early collectors talk about, or even for modern folks, like you don't want to etch things for too long because then you get a chunk of crystal that might fall out, and other challenges like this. So this specimen was collected by a guy named Carl Blyfus. We got it in 1931. The UC Museum of Paleontology Archives describes Blyfus as the San Benito County jailer in 1941, and then also says that he maintained the largest amateur fossil collection in California. So I haven't been able to find a lot of information about him, but we do see some specimens of his, this shark tooth and this clamshell in the Pacific Grove Museum of Natural History. So, a friend of ours a little bit down the coast, they have a number of other specimens, and he's referenced it as being like a butcher, as being like a hunter, as being like a jailer, who then also has these references in geological papers from the time, sharing specimens of people, giving things to the Museum of Paleontology and things like this. The other specimen that we're really pleased to be able to share with the community through this event, because normally this guy is on storage, and was also featured in our blog last month, or this month, both months, is this specimen here, which doesn't have quite the same like large chunky like benitoite blue crystals, but still has a beautiful sparkle to it. And it really sort of like, the pictures don't prepare you for how cool the actual specimens are. And then this particular specimen has been in our museum since 1938 or so. You can see the accession records here, and you can see these other records are different labels from J. Gisler and Son, or Julius Gisler, who was the original collector for this specimen. So as a young man, he was a mountain climbing guide in the Swiss Alps and got really into minerals when he was like guiding geologists and got really interested in the things that they found. He relocated to San Francisco in about 1914 and was working as a cook in a restaurant while starting his mineral business on the side, and grew it, and was joined by his son and ended up being famed somewhat for his self-collected benitoite specimen. So he and his son were hanging out looking for benitoite out in San Benito County in the 1940s, and there's even a story about how there was a fire that swept through the area in the late 1940s, and these two just wouldn't quit it. We've talked a little bit about these two specimens, one being on display and one not, and the one that has been on display has been there since 1985, which is the same year that benitoite, because of its beauty and its rarity and its uniquely California gem quality crystals, was made the state gem in October 1st of 1985. And now I'm going to stop my screen to invite Dr. Hilde Schwartz to dig a little bit more into the natural history aspects of the benitoite story.
All right. Any questions before I get started?
I just have to say that, Kathleen, I lament that you do everything digitally now, looking at those collections cards and that ledger and that handwriting. It's like,
oh yeah,
it's of a bygone era.
And actually the Mineralogical Label Archive that I pulled those notes from is actually this huge archive of all these different collectors from all over the United States. And whoever has been building that has been doing little biographies. So if you ever encounter anything in a small or big museum or in your personal collection and you're curious about a label, you should check that out.
Yeah, love labels.
okay. Can I get going?
Yes, indeed.
I will get going. Okay. So Kathleen has given you a great introduction to benitoite, including some of the minerals it's found with when it became a state gem. And it's a beautiful mineral. And before I start, I have to confess that I'm a sedimentologist and a vertebrate paleontologist. I am not at all a mineralogist, but I've always loved minerals. I loved mineralogy when I took it as a geology undergraduate a long time ago. And benitoite has been on my radar for a long time because I've been lucky enough to get to work not at the mine where it's found, but in the region where it's found. So I've heard a lot about it. And I've acquired a few pieces over the year from miners who have worked out on Joaquin Ridge, which I'll talk about in a minute. So it's a pretty amazing mineral. And when you figure out how it forms, it even seems more amazing. It's kind of a miracle that we have this mineral in California. I think it's very cool that benitoite is the state gem and that serpentine is the state rock. So benitoite is the state gem because it's beautiful and it's rare. And the only gem grade quality benitoite occurs in basically one location in California. And that's amazing. It's very precious. Serpentine was voted the state rock, I think, in 1965 or something like that. And that's for the exact opposite reason, not that it's not beautiful, but because it's so abundant. It's kind of it's a classic California rock, especially in Central California. It shows up all over the place. If you drive up 280 between Santa Cruz and San Francisco, you see serpentine popping out on the sides of the highway. And if you go to a good locality, I brought one of my favorite pieces of serpentine with me. Serpentine is from the beach south of 20 miles south of Big Sur. It's shiny and glassy. It's really pretty. So it also gets beauty points. So this is abundant. This is not abundant. But the cool thing about it is that these guys are two peas in a pod because they co-occur. Where benitoite, the one location where benitoite occurs, there's a lot of serpentine. And they formed in different ways, but their histories are tied together. So I'm going to try and explain that. And I'm going to have to talk about plate tectonics. So if you hate plate tectonics, I apologize. So we'll start with today. What's going on today geologically in Central California? So we have a major plate boundary between two tectonic plates that runs through our state. Here's Santa Cruz. We're up here right now. And we sit on the Pacific plate. The plate to the east of us is the North American plate. It's separated by the San Andreas Fault, which is a major plate boundary. And the sense of motion, the relative motion of the two plates on either side of the San Andreas is as shown by the arrows. So our Pacific plate is moving, there goes the lighting, moving to the northwest, and the North American plate relative to the Pacific plate is moving to the southeast because of the way this fault is moving. It's a strike slip type fault. So that's today. So of course, there are certain types of processes that are associated with strike slip faults, including, as we all know, earthquakes. So I put on these little exploding stars to represent earthquakes. You notice on this map, this is a geologic map of our part of California, that the rock types shown are different colors on the west side of the fault than on the east side of the fault, because the west side has moved so far relative to the east side that it's brought rocks up from the south and then smashed them together with rocks that were in place in the north. And you have a big geologic discontinuity across that boundary. All right, so the range directly east of the San Andreas to the southeast of us is called the Diablo Range. So this is the range that's east of San Jose. It extends from Mount Diablo up in the north, which is north of where this map shows, goes all the way up to the Delta, all the way down to Coalinga down here in the south. So the sole locality for gem quality benitoite is found in this blob here. This is the pod that the two peas are in here, this purpley green blob. And that's in the southern Diablo Range. And it's up on a high ridge, maybe 4,000 plus feet high. And it's known as Joaquin Ridge. And some people also call it the New Idria Serpentine Dome because there's so much serpentine in it. And this is a little rotating benitoite crystal. It's a signal that it's the location of the benitoite mine. So benitoite and serpentine and other stuff occur in here. So this is today. Between 200 million years ago and 15 million years ago, there was a whole different geologic situation in Central California. Instead of having a strike slip fault, instead of having the San Andreas, there was a subduction zone, which is shown here. And again, I have exploding stars to indicate faulting. So in this subduction zone, the Pacific plate was still far off to the west, and the oceanic plate that was getting subducted or shoved down underneath the continent is called the Farallon plate, getting shoved under the North American plate. I've put the general location of Santa Cruz just for reference. So during this time period, Santa Cruz was mostly underwater. It was covered by water. It was in a marine setting. The subduction zone caused earthquakes as the subducting plate got deeper. At times, at least between 250 million years and 15 million years ago, that plate partially melted, leading to the production of magma, which led to a chain of volcanoes on the surface above this melting. And the roots of those volcanoes are now exposed as the Sierra Nevada range. But that other process that happened in this setting before the San Andreas was metamorphism of junk, of pieces of oceanic crust and oceanic sediments and stuff onto the edge of the North American plate. So as this plate was going down, this is not a smooth process. It didn't go down without a fight. So through faulting, at times and in places, pieces of this oceanic crust was added to the continent. And that's what this pile of stuff is here. And so here, this is the relative motion of the North American Farallon plates before the San Andreas came along. So another big process, in order to understand benitoite, we have to consider what happens here at this subduction zone. So where this plate is subducting, there's a great deal of pressure, very high pressure, and that caused metamorphism. Metamorphism are processes that change rocks from one type of rock to another type of rock without melting them at either very high pressures or very high temperatures or both. So in this subduction zone setting, it was very high pressures. So oceanic crust was getting added to the continent here through faulting. Metamorphism was happening to the oceanic crust and other junk, maybe sediments that are getting carried across this ocean basin over here. Faults were developing in here and so on. So this is a very active part of the subduction zone. And the serpentine that occurs today in Joaquin Ridge and the processes that ultimately led to the formation of benitoite are related to this setting. Okay, in the next slide, I'm going to show you a cross-section through the oceanic crust, and it's going to be approximately the cross-section that is shown by this box. Okay, so here's a kind of a boring picture of oceanic crust. There's some sediments on the top, and then there's some pillow lavas, and all this stuff in here is basically the composition of the rock basalt, which is a black volcanic rock. The base of the oceanic crust, rather than being made of basalt, gets richer in olivine and the upper mantle. Finally, it comes into contact with the upper mantle, which is also rich in olivine. And I'm telling you this because I want you to know the subduction zone, the metamorphic processes of the subduction zone, the very high pressure processes, had the effect over time, over that big time span, almost 200 million years, of affecting some pieces of oceanic crust, the basaltic part, by changing them into a rock called blue schist, which is a very common Californian rock. And the deeper parts of the oceanic crust and even maybe pieces of the upper mantle, where they came into contact with water, and there's a lot of water in sediments and pore spaces and rocks that are under the ocean that are getting subducted. These olivine-rich rocks, which are further down in the crust, got turned into the mineral serpentine and into the rock serpentinite. So the metamorphism at that leading edge of the subduction zone is responsible for these two rock types. They're really different in some ways, which you need to understand benitoite. So blue schist, when you make the transition, the metamorphic process that turns basalt into blue schist, produces something that is much denser. The blue schist is much denser than the basalt that it's made from, high pressure. Okay. So, however, the olivine-rich rocks at the base of the oceanic crust, when you add water to them and they metamorphose into serpentine, end up producing a rock that is much less dense than the original olivine-rich rock, which is weird. It's a weird kind of metamorphism. And it leads to an odd situation in the Earth's crust, where instead of having very heavy and dense rocks deep below the surface, now you've suddenly taken those rocks, changed them into something that have a greater volume and a lower density. And they they are unhappy down there. They should really be at a higher level in the crust. And often these rocks will find ways through fractures, faults, to work their way up through the crust to get closer to the surface. Okay, so here's the deal with benitoite. So in this period, at 200 million years, there's subduction. There's no San Andreas fault yet, and there's ongoing metamorphism of the oceanic crust that gets into the subduction zone. So serpentine and blue schist are created, and serpentine begins to rise at times, at least rise up through the crust because it's so low density. And I have that depicted. I have that depicted by this green line. The green line is meant to show serpentine, and the little blue blocks are pieces of blue schist blocks that get kind of pulled along with the serpentine as it rises up. So the New Idria serpentine dome has a lot of serpentine, but it also has blocks of blue schist that were metamorphosed in a similar environment, but to a very different effect. They're very dense, but they got caught up with the serpentine, and they have eventually risen to the surface. About 27 million years ago, the San Andreas fault was born. I say that facetiously. It's not a very good geological term, but it gets the point across. It started forming, but it started forming down in Southern California. So it started in, we'll say in LA, and then it spread. The San Andreas, once it started forming, unzipped like a zipper, and it migrated towards the south and towards the north, to the north, the southeast, and to the northwest. So about 12 million years ago, the San Andreas fault got to our latitude, and it shut down the subduction zone. So the plate boundary, the tectonic plate boundary, changed from subduction, convergence, to strike slip motion. And when that happened, when the San Andreas met the subduction zone, there is a lot of excitement. And one of the things that happened was that brought a lot of heat to the area. And that heat produced hot waters, hot fluids known as hydrothermal fluids, enriched in elements that were made from the interaction of those hot waters, broke down minerals in the previously formed rocks in the serpentine, in sandstones near the serpentine, and blue schist blocks, freed up those elements, and then those elements got in places very concentrated and themselves precipitated as minerals. And benitoite is one of the minerals that precipitated in veins about 12 million years ago that formed when the San Andreas took over from the subduction zone that had preceded it. And the veins of the benitoite veins always form in fractured blue schist. So blue schist is that upper part of oceanic crust that got metamorphosed near the old convergent plate boundary, and then got plucked up by a serpentine rising through the crust, which is a weird thing to think about. And then later, as lots of hydrothermal fluids fractured both the blue schist and the serpentine, new minerals formed in those fractures. And this is a little diagram showing a tiny little baby mineral in a hydrothermal fluid, finding cations and anions that can make it grow bigger and plucking them and growing into a big mineral, which could be a benitoite crystal growing on the side of a fracture. So here's the result. This is blue schist that's part of a block in the New Idria serpentine body. This is the blue schist that got formed originally in the subduction zone, then got pulled up as part of the serpentine, and then benitoite crystal grew on it much later. So the benitoite is young, at least according to everybody that I know that has tried to figure out the age. It's probably around 12, maybe 14 to 12 million years old, which to a geologist is young. The blue schist that it formed on is old. It's probably at least 100 million years old, could be older. So these rocks are always associated in this one place in the world where you find good gem quality benitoite. And
Can I
here's
ask
another
a clarifying question?
Yes.
So, because you said that blue schist is all over the place, it's really common.
No, I said in California, we have a lot of blue schist. It's not as common as serpentine.
Okay. So, and all of the blue schist comes up through that process of coming up with serpentine. But
no, that's not true.
Okay.
It did in the New Idria serpentine dome.
Okay.
No,
And so that's why you find benitoite in that blue schist, is because it came up in that way, whereas the other blue schist.
So here's I'm going to get to the next slide, and hold on one second.
Okay.
I think maybe in the next slide, I'm going to say something about that. So this just illustrates again, the blue, here's blue schist and here's benitoite. So you don't find, even though the benitoite forms very close to the serpentine in the Nuidria serpentine zone dome, it always forms in fractures in the blue schist within the serpentine. So blue schist doesn't always, it's not just here because of that process. It isn't always associated with serpentine, but in many places it is. But there's a lot of mineralization. This is that serpentine dome again, shown in a little bit nicer illustration in this 1997 paper. The blue colors are serpentine. There are little blocks of blue schist within that, and the blocks of blue schist are where the blue stars are the benitoite mines. The biggest and original mine is to the south here, and a number of smaller mines have been identified since. The best crystals, I believe, still come from this, the original benitoite gem mine or Dallas mine. There was, when the San Andreas first arrived here, and there was a lot of hot water with minerals dissolved in it that precipitated out new minerals in these rocks, the serpentine was also mineralized. We got a different set of minerals. It didn't get any benitoite, but there were some beautiful garnet, at least two different types of garnets form in fractures in the serpentine, and a mineral called vesuvianite, which is beautiful. And so there's mineralization in the serpentine, but it's not benitoite. And the mercury from the Nuidria mercury mine, which is located over here, also formed as part of that mineralization process, perhaps at a slightly different time. And the rock that hosts that mercury is sandstone. It's neither serpentine nor blue schist. So different rock types just acquired different types of minerals about 12 million years ago through these processes. Did that pertain to your question?
Yeah, I
Marissa?
think so. Yeah,
Okay.
it just sounds to me like that. So blue schist occurs elsewhere, but this process of the hydrothermal mineralization doesn't occur.
Hydrothermal mineralization occurs all over the place all the time, but this was just a very special situation. We had the right rock types in place, and then you had this episode of lots of hydrothermal, activity that was brought on by the San Andreas fault. And then you had all these hot waters percolating up through fractures and even fracturing the rock themselves. And in different rock types, those hot waters were acquiring different types of they were breaking down different types of rocks and acquiring different types of elements. So what precipitated in veins eventually were different types of minerals in the different rock types. And blue schist tends always, pretty much always forms at subduction zone settings, but how it gets exposed at the surface can be through mechanisms other than the one I'm just describing to you. This is just for this dome.
Cool.
Okay, so benitoite is found in other places, but no place in good crystalline quality, such that you could cut it into a gemstone. So I've put some little twirling benitoite crystals here to show other parts of the world where trace amounts of benitoite have been formed, very, very, very tiny, microscopic bits of benitoite. The settings are not exactly the same as at Joaquin Ridge. It just depends on the place. So benitoite, I'm not going to belabor this, but benitoite is made, it's barium titanium silicate. This is what, if you could look in it and see the individual atoms, this is a very colorful representation of what they look like. Barium, titanium. None of these elements is particularly rare in the Earth's crust. They're all pretty abundant, and yet benitoite is quite rare. So these are elements that just don't always get together to make this beautiful crystal that has this very peculiar crystal shape. It wasn't known until the early 20th century. So Kathleen already talked about this a little bit. When benitoite formed in this blue schist, because of these hydrothermal processes, several other minerals formed along with it. Joaquinite, it's pretty brown mineral, neptunite, black mineral, and also natrolite, which was the last crystal to form in these veins. And we know that because it covers up the other crystals. And therefore it has to be dissolved away with hydrochloric acid. So here's a box of ore. from the Benitoite mine before it was processing, and you can see there's not much blue peeking through. It's mostly covered with nature light. So I'm going to just talk for a minute about things that I think are special about benitoite. And Kathleen already went over this. It was the first naturally occurring mineral found with this amazing ditrigonal, dipyramidal crystal shape. So ditrigonal, it's a three-corner thing. If you look at it on the edges, it looks like pyramids on both edges. I have a very tiny crystal, but you won't be able to see it, I'm afraid. But you can see from the pictures what I mean. There's a pyramid here, and then three corners. It's a great shape. A number of benitoite crystals have been formed in the form of twins, which happens when as crystals grow across each other or penetrate each other. And it can be at different angles. It means that the two crystals are sharing atoms within the crystal structure. And the benitoite twins are really pretty, and they often form 5 or 6, not often. The twins are rare, but when they do form, 5 or 6 pointed stars sometimes happen. This is a nickel for scale. So not all crystals do that. Some do, some don't. Benitoite is also dichroic, which means that because of the way the crystal structure is built, when you look along one crystal axis, so you can define a crystal by an X, a Y, and a Z axis to assess its three-dimensionality, its symmetry. When you look along one crystal axis, benitoite might look dark like this, and you look along another crystal axis of on the same crystal, and it might look light like this, which is cool. A lot of other minerals do that, including aquamarine. I saw that was somebody's favorite mineral. But not all minerals. Benitoite is also very sparkly. So because of its crystal structure, again, it disperses white light and breaks it up to produce different colors. And that creates highlights within the crystal. It's called fire. This is what gives diamonds their sparkle too. And it's a pretty sparkly mineral as crystals go when it's clear. And this is the kind of jewelry that can come from having that sparkly mineral. This is one of the bigger cut benitoite crystals. The largest crystals, naturally formed crystals of benitoite that I know of, and I think it has been grown in the laboratory, are about 5.5 centimeters in size. And here's an example of a crystal that's that size. This crystal is not clear, so there's no way you could cut this crystal and turn it into a gemstone like that. And that's because some benitoite crystals, as they grew out of the hydrothermal fluids that gave birth to them, they grew around other very tiny crystals that were already forming in the fluids. And those tiny crystals got incorporated into the crystal, and the fact that they're in there takes away from the clarity of the final crystal. So some benitoite crystals look like this. Maybe the best thing about benitoite of all is that it fluoresces. So benitoite is one of the prettiest, in my opinion, one of the prettiest fluorescing minerals of all the fluorescent minerals. And it fluoresces because it's probably tied to the titanium. That's why I put a little thing about titanium in the corner here. The titanium oxide structure in the crystal, the spacing between electrons and the nucleus, and some of those atoms is just right so that when you shine ultraviolet light on the crystal, it can excite some of those electrons. When they get excited, they jump into a different higher electron orbit briefly. And then when they jump back, they release some energy in the form of visible light. And that's what we're seeing in this picture. This is the visible light. This is from electrons getting excited by short wavelength light, and then getting and re-emitting some energy. So benitoite is wonderful under black light. And my room keeps, I was going to show, have my black light here. My room keeps turning the lights on against my will. So I don't think it's dark enough to show you right now, but maybe in a minute I can get it to work. So I've been working out in the area with students from UC Santa Cruz, doing field geology, mapping rocks, not at the mine, but close to it for a long time. And I've had the pleasure of getting to know some benitoite miners over the last couple of decades. And I've heard a lot of wild stories about benitoite. So these are unscientific special facts about benitoite, in addition to its real scientific qualities that I just discussed. I have met people, more than one, who believe that benitoite can be used to communicate with extraterrestrials. I don't know why. I have also heard a number of people tell me that crystalline benitoite, and it's only found in this one area, right, attracts UAPs, and that's unexplained aerial phenomena, the new term for UFOs, because aliens use it as it's a key fuel for alien spacecraft. That's hard to prove. And I've also heard stories of people who are pretty sure out there that they've gotten abducted because aliens are attracted to that area because of the benitoite. They all came back, so that's a good sign. I'm not endorsing these ideas. I'm just telling you what I hear around the campfire. So there are two types of mines. There are two types of mines up on Joaquin Ridge. Of course, the one that Kathleen talked about is the lode mine, the hard rock mine, which started off with the original finder finding jewels, but also this is an account from a book that his son wrote about claiming he walked into a little cave in the side of a hill and just saw all this stuff glittering in the walls, which is pretty compelling. I would start digging at that point too. So lode mining or hard rock mining is a lot of work, right? Hammer and tongs kind of work. But there are also placer mines up on the mountain. And placer mines are mines typically in creeks. And there's a little creek shown in this picture. This is the Andy mine. And they're creeks that run out of the drainages close to the main mine. So you can see that there are drainages up here. There's water running around. That water can pick up crystals and carry them downstream. And then if you go out at night with a black light, you might be able to find some stuff just by sifting through the stream deposits. So people actually have claims, placer claims, up on the ridge. And there has been, since the time I have been working out there, I have heard many stories and have witnessed friendships break up because of high grading. High grading, of course, is when you go behind somebody's back onto their claim and take their good stuff. And it is very remote out here. All of the people that have gone up, like George Lauterbach, people that preceded him, this is no just waltz in the park to get up to the site. It is really remote and it's hard work to get up here. It's high, it's rugged. So it's hard. It's a hard place to keep an eye on your stuff all the time. It's easy for people to sneak in and steal other people's benitoite. And that there's been a lot of that that's gone on. And it is considered a shooting offense, I think, in that part of the world. So it's really not a good idea. I wanted to mention briefly that there's another mineral that sounds a lot like benitoite. It's called bentonite. And I'm showing you a picture here from Petrified Forest National Park, where I used to work on these sedimentary rocks, which happen to have dinosaurs in them. These lighter layers that I'm showing here are made up of a clay mineral called bentonite. So bentonite's a particular group, belongs to a particular group of clays that are called swelling clays, mixed layer clays. And when they get wet, that means they can take up a lot of water in the crystal structure and they swell. And then when they dry out, they dehydrate, they go back down again. So for this reason, when you drive, if you've ever driven to the Petrified Forest or beyond it towards New Mexico, you might have noticed that Interstate 40 in places is like a roller coaster like this. And that's because there are a lot of bentonite layers underneath the surface, underneath the road. And seasonally, those clays are shrinking and swelling and shrinking and swelling. And it's really hard on infrastructure. It can destroy people's houses. It's a constant road problem. But that's bentonite. So not benitoite. Benitoite would never cause a problem like that. And I think that's all I have to say right now, unless people have questions. I have a few suggestions. If you're interested in learning more about the mineral, this paper on the top is a great paper. You can just Google the name and it will pop up for you on the internet. These two sources are also really interesting. You can get this, it's a little bit hard to do. I am still looking for this. I would love to get a copy of this someday. But there's a lot out there that you can look at.
And I'll send an email to everyone who registered afterwards with some other links to resources that the museum has put together. And I can include this New Adria paper as well in that. And it doesn't look like we have a lot of questions coming in from the chat yet, but for everyone out there, feel free to write down your burning questions and concerns. I know that me and Kathleen, though, would love to keep chatting, that we've got some questions for you, Hilde. So we're coming up on 7, but we'll stick around for several more minutes to do questions. And we did actually just get one in from Marlene, similar to what Mary was asking about earlier, which is, are any of the mines still active? And it sounds like, Hilde, you have experience, working with or spending time around campfires with some current miners. So could you speak a little bit more about that?
Okay. So the main gem mine is no longer active, but the last I heard, and Kathleen, I think you had a picture of this maybe in one of your slides at one time. Some years ago, the owners of that mine decided to load up just raw ore out of the mine and take it down close to Coalinga, and then charge people money to sift through it and see if they could find some benitoite. And there was some kind of a deal where if you found a crystal bigger than a certain size, you had to hand it over. You got a cut of the profits, but if you found small crystals, you could keep them. But as far as I know, that mine is no longer active. The placer claims, I believe, still can be claimed, but all right, I forgot the end slide. Most important one.
The other thing I wanted to add to that is that there is the article about the benitoite from the New Adria mining district is a great read, high recommend. And it does the main vein, an extension of it was discovered after like years of not being aware of it in 1997. So that's like 100 years from its initial discovery. There just was a thought that there was like nothing of that sort of scale left, and then it was rediscovered in 1997. So I think that yeah, now they mostly do things where people are able to like go through the tailings, and I think they recently reopened post-COVID by appointment.
Yeah. So there's no doubt a lot of minerals underneath that ridge still, but the question is, can you access them? It's all about accessibility. There's all kinds of stuff under that hill, lots of it. So in the right on this is a picture of one of my field geology classes out near Joaquin Ridge, and the person standing on the right here, who is sadly now passed away, had a claim for that and for the Andy placer mine for a long time. And so he, at his house, which was just to the north of the town of New Adria, not up on the ridge itself, he brings stuff down here and then do his processing on his property. And I used to take my class there every year to talk to him. He'd show us his latest great finds, and that was great fun. But he passed away a couple of years ago, so it's very sad. And in the previous picture, previous to that person, this is another former miner who now I think lives in Nevada, who had claims on both, I think, a benitoite placer mine, and he had a claim on a demantoid garnet mine, which is a type of very sparkly garnet found in veins in the serpentine, close to one of the blue schist blocks. So yes, both of these guys used to come and hang out at our campfires when I was out there with students. So I heard a lot of stories.
He reminds me of my uncle, who is a gold miner. He's a placer gold miner, and he looks a lot like this.
There's a look. There's a look, right? There's kind of a look.
Yeah.
That makes me wonder, and I see that there was a question in the chat, and it was first discovered at this main mining location that we're talking about, benitoite. There was a question about if it was here or elsewhere, and that is where it was first discovered. Yeah. And then I also, when it was first discovered, there's this story of like James Couch, like maybe like, writing quickly on horseback to register the mining claim, like one of these sort of fly-by-night moments to make sure that they could get the claim after it was discovered. And I was wondering, Hilde, if you're a little bit more familiar with that claim process or how that, like.
I really am not.
Okay.
I'm not. But I can imagine that he rode fast, because I do know something that when the mercury mine, the New Idria mercury mine, which is named after the New Idria, pronounced differently, mine in Slovenia, which was one of the two great mercury mines in Europe before this mine was discovered. These mines are out really in the middle of nowhere. There is a paved road that goes from Hollister that you can take out through big old San Diego County that ends at New Idria town. And to get up on the dome now, probably is a lot like having to get up on the dome in the early 20th century. You can use a car, but you need 4-wheel drive, and really a horse would be preferable because there's a lot of tricky places in the road. But because there were mines out here and this area was remote, it attracted banditos. And that started back in the 1850s with the mercury mine. So it was dangerous. Like if you had anything of value, including flasks of mercury, you didn't want to dilly-dally between getting them from the mine back into town, into Monterey or wherever it was you're going to try and sell stuff. So I have nothing but respect for people who were doing geological surveys and mineral surveys and making all these discoveries up on this ridge, because it is rugged territory. It was rugged. It was rugged in terms of just moving around, and it was dangerous. And it's hot. It's so hot out there in the summer. So,
is that still the work of geologists like yourself? You said that you spent time in the field with your classes. Is it often kind of rugged and unruly for you?
Yes, it is. I have a no whining class with my students, but it's hard. It can be hard. We were out the last time, which was just a couple of weeks ago, out in that area. I took a copy of one person's account of the first geological survey of California, a guy named Brewer, who was part of the survey. And I read them the chapter where he travels through, he and his colleagues, which included Josiah Whitney, who was the head of the California Geologic Survey at the time. And he's describing the mine. They get a tour of the mercury mine. Of course, there's no benitoite known at that time, but they go around at the top of the ridge looking at their other little mineral occurrences. But most of the time they're out there in July. Most of the time he spends talking about how it's so hot, and then it's just so much hotter. Next day, it's even hotter. It's even hotter. Like the mules are dying because it's so hot. It's intense. So, but money is a great motivator.
Yeah.
I love that though, like early scientific writing, when you see the really like human, like daily suffering part of it, when they're like, actually, this is really annoying, or that Darwin quote that's been circling relatively recently, where he's basically like, I hate everything and I'm really bored today and I don't want to write this paper. He's like,
and I'm very stupid. I think he says
he's like, this is all really stupid stuff.
I think Brewer ended his chapter on New Idria, the New Idria area. He talks about how the miners suffered because, especially the miners that had to clean out they mined the ore, threw it into furnaces, because you can break the bond between mercury and sulfur at pretty low temperatures. And then the mercury, you get a mercury aerosol, and then you can turn it back into a liquid. And so that was all done in a furnace, but there are these guys that had to go in and then shovel out the ore. And meanwhile, there's mercury vapor in the air, and people got horribly sick and died all the time, but they made such good money. But there was never a shortage of the supply of people willing to do that. And Brewer says at the end of his chapter something like, and thus do the capitalists of the world, like, make their money on the backs of, like the poor and needy. So it's rather eloquent.
Yeah.
19th century writing, as you say.
Well, and so many of the people who came out for the gold rush and helped out with cinnabar and looked for benitoite, they didn't make their riches or their quick buck. They made a very,
Not with
very,
gold,
very
but
hard work buck.
That's true. So it was an amazing coincidence that the cinnabar mines, the mercury mines, were discovered when they were. So they were discovered right after gold was discovered, both New Almaden and New Adria. And before that, the mercury market in the world was, most of the mercury in the world came from Europe, from the Almaden mine in Spain and the Adria mine in Slovenia. And it was controlled by one family, all that mercury. And the gold miners really needed it because it was the most efficient way of separating gold, say in a sluice, to get it to amalgamate with mercury. So if those two mines hadn't been discovered in California, not nearly as much money would have been made in the gold fields because mercury would have been so much more expensive to purchase.
It's so interesting how they all kind of
really interesting coincidence. Yeah.
We did have a couple of questions come through the Q&A. And this one is maybe in response to when you were talking about how benitoite fluoresces. And they're curious specifically, is serpentine, does it fluoresce or is it radioactive? Or does serpentine have any special qualities like that?
All minerals have special qualities. They're like children. That's worse. Serpentine is really shiny. It doesn't fluoresce, but it can't, and it's not inherently radioactive. It doesn't have any pure serpentine. It doesn't have any radioactive elements in it, but every mineral can have elements substitute into it while it's forming. Most minerals aren't pure and 100% what their pure mineral formula says they are, because nature's messy and accidents happen. So often minerals have a little bit of this, a little bit of that, but as long as the main structure is what the formula says, then it gets to be called that mineral. So it's possible, I think that is very possible, and I'm sure true, that in places radioactive elements have found their way into serpentine, and definitely other minerals too, but it's not inherent. Asbestos is a form of serpentine, right? You may or may not know. And about a third of the New Adria serpentine dome at the surface, the south end, is made of asbestos. It's made of chrysotile asbestos.
Sounds like a very hazardous place.
It's a very fun place. Got it. Snakes, heat, asbestos, banditos.
Capitalists.
Yeah. High graders. Yeah.
Aliens.
Aliens.
And then Donna's curious about, is it currently on display in Santa Cruz? And so I think maybe there's like two answers to that. So like one is that benitoite doesn't naturally occur in Santa Cruz that we know of.
It occurs in your museum.
Yes,
sure.
But it is on display in Santa Cruz because you can come visit it at the museum, and the museum's now open. So you can visit us Tuesday through Sunday, 11 to 3, and you can see benitoite in the flesh at the museum. And is there also benitoite on display within the halls of the Earth and Planetary Sciences?
The hallowed halls of the Earth and Planetary Sciences Department also has some, I don't want to undercut you on this one, but we do also have some benitoite on display. We have a bunch of mineral cabinets, and there's several pieces of our benitoite that you could come and see, but not right now because we're still in COVID mode on campus. So the buildings are perpetually locked unless you have a key. In the fall, things are going to open up again.
Maybe this would be a good time then for you could you potentially try to see if you can get your samples there to fluoresce for us, since you pulled them out special?
Oh, we can also sure.
Cool.
I think there's a mineral called papsite, which was discovered at Calcar Quarry. Marisa and I just talked about the pronunciation of this place. That's really similar to benitoite. It doesn't have a lot of these same qualities, but it's has a very similar composition. So, new minerals are discovered in this area.
Yeah. I guess I was also thinking about with how, so like we call our state gemstone is benitoite because it's the only place where gem quality mineral of benitoite has been found. But the other places that it exists over the world, is that it's not gem quality because it's got that other stuff in it, like you were talking about, Hilde? Like, is it that
Okay,
it's
wait a minute.
cloudy?
No, it's tiny. It doesn't, it just, the
Oh.
crystals are so tiny, they're like dust.
Okay. So
In
it just
fact, in a
doesn't
couple
differ.
of places, including Belgium, they thought they'd found very tiny crystals of benitoite. It turned out to be a clay mineral. I mean, that's how small.
Oh, wow.
We're talking about very tiny.
Okay, I'm
I don't know
sorry.
if you can.
Yeah.
Okay, this is hard.
That's
I've never been good at this. Okay, there we go. It's so close to the screen. How's the black light? Can you see? Yeah, you
It's
can see it.
good.
Yeah.
It's
Yeah.
good.
Awesome. So this is not a particularly gorgeous sample when you look at it without the black light, but once you put the black light on, it gets a lot prettier.
I'd take it.
Yeah, it's pretty nice. Yeah, this got picked up from one of the placer mines, from a miner I know.
so cool. So the not all of it is fluorescing. Only parts of it appeared to be fluorescing.
Only the benitoite is fluorescing. The blue schist is not fluorescing. The natrolite is not fluorescing. And the neptunite is not fluorescing. It's just the benitoite.
Nice. And Kathleen, have you tried to fluoresce ours?
Huh?
So
I was asking Kathleen if she's put ours under a black light.
I have put the one that's in collection storage on a black light. It's a little bit harder to get. Yeah, I think I need a more powerful one because we didn't get a strong response. And it was right around the same time that I learned that sometimes in preserved taxidermy specimens, specifically ducks, they have naturally occurring oils that are sometimes removed in the taxidermy process. But if they're not, you can actually get older taxidermy specimens to fluoresce.
Platypuses fluoresce, live ones.
Ah,
And
okay.
scorpions.
And I did know about scorpions. So we need a stronger black light because this is about to revolutionize our Halloween displays.
Yeah.
I can give you a tip. So there are different wavelengths of ultraviolet radiation. Benitoite only fluoresces under the shorter wavelength.
Ah,
If you just go and buy a regular black light, you're going to get the longer wavelength.
I missed that.
Yes, so some minerals like fluorite, the mineral fluorite, will fluoresce under the longer wavelength, which on mine is about 365 nanometers. But to get benitoite to fluoresce, you need black light that's more like 250 nanometers. And those are more expensive, the lights that generate the shorter wavelength. And especially
anyone would like to sponsor our black light needs.
My light has both wavelengths built into one. So I could have the shorter on, the longer wavelength on, or both on at the same time.
Oof.
But I catch everything, which is really fun.
I want to do a black light like night walk for the museum at some point and see what we can find.
That would be great.
With that. And we'll be bringing back our blacklight room for Halloween this year, if all goes well. So maybe we'll bring the benitoite for that.
I think that's a great idea.
Yeah. Let's see, Kathleen, do you have any other questions for Hilde?
I think that we covered most of the things that we really wanted to talk about today. I know that Hilde, you were wanting to be sort of careful with the sort of campfire stories that you had learned from folks. But I appreciate you sharing them here today. I feel like maybe we're getting towards the end here, Marisa, did we want to sort of end on our final, what are our favorite places to go for a local geology question?
Let's end on that. And if you if you're attending tonight and you are communicating with us via chat, write your favorite places in the chat as well. Where do you want to go to look at geology? Where's your favorite place?
We're talking about local, right? Local Santa Cruz.
Maybe
area?
like kind of like a day trip. Make it a little broader. Why not? That's accessible. So not something that you're going to get shot if you are found exploring.
Right. That's very important, not to trespass. Well, I'd say for local geology, if I have somebody who's coming and visiting from out of town or from another country, the first place that I take them is Point Lobos, hands down. Because the geology is amazing and it's so beautiful. And it's pretty easy to get to. So I don't know if you guys have been there.
Yeah. Can you give us one highlight of the geology of Point Lobos?
Okay, I will. So Point Lobos is just south of the Monterey Submarine Canyon, right, which is a huge submarine canyon. The rocks of Point Lobos there's granite there, and there are sedimentary rocks. The granite's about 100 million years old. And the sedimentary rocks, which include beautiful conglomerates with big cobbles and sandstone and some shaly units that have lots of interesting trace fossils in them, are about 55 million years old. And the setting is this: the granite represents an ancient submarine canyon. So the granite was formed at depth, uplifted, cut into a submarine canyon 55 million years ago, and then filled in with this very complicated and now beautifully exposed pile of sediments. And in the meantime, it's uplifted on the coast, sitting right next to one of the world's most amazing submarine canyons that is active today. Isn't that a wild coincidence?
So poetic. Comes
Yeah.
full circle. I love it. Okay, that's my next day trip. Kathleen, do you have a favorite place to go explore geology?
Point Lobos is also a big one for me, especially like I used to go there when I was younger, and before I was better at like understanding reading signs and following, respecting, the regulations on where you should go. My siblings and I accidentally wandered like into parts of the tide pool structure that we were not supposed to be, and encountered a whole bunch of geologists who worked for Shell Oil. And
go down there all the time to study the architecture of submarine canyons.
And it was a really interesting experience because so they like saw us and I think thought that we were coming there to heckle them maybe or something, and they were like, hey, we have permits, and we were like, ooh, if you're saying that to a group of teenagers, then we probably shouldn't be here. And it was a cordial encounter, and they told us some things that actually started. That I think was the first time that I read up on the geology of that area, because I was like, oh, this is clearly something worth careful looking at. And then we wandered back away to the tide pools that we were allowed to be at, and had a lovely, lovely day.
I love that tide pooling, like people think of tide pooling as a biological experience, but it's also a geologic experience, which is very cool. Sarah shared Ring Mountain, which has a lot of cool metamorphic rocks like blue schist and
serpentine. Which is serpentine. Yep.
I don't know if I've been there. I really like, Hilde actually showed me and Kathleen on separate occasions, the Swift Street outcrop. Both Kathleen and I went through the California Naturalist program, and Hilde leads field trips for that. So if you ever have the opportunity to go through that certification, I highly recommend it. And the Swift Street outcrop is on West Cliff Drive in the city of Santa Cruz. And you just kind of like tumble down a little dirt path. And then there you are in this like beautiful display of a variety of local Santa Cruz formations and phenomena. And you can kind of see like faults in action and chemical sedimentary rocks and fossils, and it's just right there, and it's a great place to sit and read, fish. So yeah, lots of great geology all around us. And we talk about geology every month for the Rock and Pop-Up. I'm going to share links to some relevant Rock and Pop-Up videos that we do with Gavin Piccioni and Graham Edwards, who also work with Hilde up at UC Santa Cruz. And I'm going to share links to some of those with you guys after this, as well as some other resources. And our next Rock and Pop-Up in July is actually going to be our very last in-person Rock and Pop-Up that we are ever going to have, because one of our geology gents is going on to other things, not bigger and better things. There's nothing bigger and better than being a geology gent for the museum. He's actually going to stay as a geology gent virtually, but on July 10th, I believe, they're going to be in person at the museum identifying rocks. So stay.
Yeah, tell your friends. They're really good.
They're so
everybody.
Good. Okay, well, we've more than overstayed our welcome. So I'm going to say goodbye. Yeah, so Hilde, thank you so very much. This is fascinating. Thank you, Kathleen, as always. And until the next time, I'm sure we'll find another. Last time we had you talked about dinosaurs. This time, Benitoite.
I'm looking forward to Halloween now.
Yes. We'll see you at Halloween. All right.
Blacklight room.
Okay.
you go.
Good night, everyone. Thank you so much.
All right. Bye-bye.
Bye.